Hello everyone, I'm Chirinio and come from Capital Normal University of China. It's my honor to present our work. The topic of our paper is BDFNet, a boundary isolate and discriminative feature extraction network for COVID-19 non-infection segmentation. I will talk about it from the following four parts. The first part is background. It has been reported that Chinese CT play a crucial role in first-line aid of COVID-19. From a clinical point of view, COVID-19 has rich imaging features in CT which can reflect the patient's infection region and the degree of infection. Most hospitals have applied CT in research and later follow-up treatment. However, there are still difficult problems with the segmentation of the lesion area of COVID-19. First, at present, the public available COVID-19 dataset is limited. A neural network with a simple structure is easy to overfit. Second, the infection layers vary greatly in shape, size, and texture at different infection stage and among different patients, such as GGO in the early infection stage and the primary consolidation in the later infection stage. For example, the boundaries of GGO have low construct and irregular shape as shown in the right pictures. To address the above issue, we propose BDFNet to segment COVID-19 non-infection from CT images. Our contributions are as follows. First, we propose a neutral network BDFNet with a double branch structure for the infection area of COVID-19, and propose the adaptive feature fusion model, which can model the complementary relationship between the texture features and shape features based on the location of the infection area and use the boundary features as pure infection to enhance the boundary of the segmented area, and propose the triple attention model to extract discriminative features from limited data for eliminating the shortage of annotation data. Next part is our method. As shown in the right picture, BDFNet consists of two branches. The first branch of the network, named the text branch, is a regular segmentation neural network, and the second branch, named the shape branch, processes the shape information in the form of the layer region's boundaries. We enforce the shape branch to only extract boundary-related information by using a dedicated loss function as supervisor. Finally, the features, especially those with precise boundaries, is produced by fusing the texture features from the text branch and the shape features from the shape branch. Here, we fit CT image into text branch and obtain high-level features denoted as N1, N2, N3, where the 1, 2, 3 indicate the text branch at culture level. The fused features are computed by algorithm N1, N2, N3. Then fused features combine with each of the feature maps at different levels, which is fed into the TA model and the AFF models. To obtain the texture and the shape features in an then-to-then manner, we use the standard BCE loss function to constrain the boundary prediction. To learn the semantic representation of texture, this loss function is used for each segmentation output supervisor. Finally, we propose the joint loss function, which composes of the boundary segmentation loss and the segmentation output loss. Here, lambda is the weight to balance the different loss and be set to 1. Intuitively, the model trained with joint loss could learn to predict individual pixel values in infection regions boundary correctly by L boundary, and also learn to locate infection regions through LDs. Next, introduce the TA model. As shown in the picture A, TA model will obtain rich contextual dependence and improve the feature representation by modeling in interdependence in the spatial dimension, channel dimension, and the spatial channel dimension. Then we concatenate them and apply a convolution layer to obtain the final output. The structure of each attention model will be introduced later. As shown in the picture, for the PA model, we reshape the input feature maps into the required dimensions. For feature maps A and B, use the matrix multiplication calculation and then activate by softmax. Multiply the activate feature maps S with the feature map C and add the generate feature map with the original feature map X to get the final output result. Here, R is a linear scale parameter. For the same model, similar operations are performed. The only difference is that the input dimensions are different from the PA model. Apart from this, we also design an instruction attention model to build a cross-dimension dependence between the channel dimension and the spatial dimension. As illustrated in the picture, firstly, the input feature X was reshaped to H and G by permuting and max pooling operation. Then, we apply matrix multiplication between H and G and calculate the cross-dimension activation map key by utilizing softmax layer. Then, we performed event-wise multiplication between the generated attention map with the feature generated from the convolution layer. The output is applied to feature dimension adjustment and the element-wise addition with the original X, feature X. Here, V and conv denoted feature dimension adjustment and convolution. Next, introduce the FF model. As illustrated in picture, given the text features M texture and the shape features M shape. First, the mapping function L is obtained by FF model based on the shape features to produce a set of affine transformation parameters ipsu and dirt. It can be expressed as the follow formulation. Then, we make the resolution of the texture features sum as the shape features by upsampling operation. Finally, the generated features are element-wise multiplied by ipsu and then element-wise summed by dirt. Therefore, the output of each FF model, M output, can be represented as follows. Based on the FF model, the BDFNet could use texture information and shape information and compensate for the lost infection boundary related information to generate segmentation results with more precise boundaries. The next is the experimental part. As shown in the picture, implementation details are as follows. We use the Python 1.3 to implement the entire model. We conduct application studies on the different designs to prove the effectiveness of our BDFNet, including the TA model and the AFF model. Table 1 and Table 2 shows the segmentation performance of networks with different posted components on COVID-19 CT selected site and CC2 site. The experimental results verify the effectiveness of our posted model. At the same time, we also compared with other algorithms. Table 4 and Table 5 show the results on COVID-19 CT selected site and CC2 site. Although it didn't achieve the best performance in all metrics, but it achieved the best performance on the 2 datasets on the most important this metric. This shows that BDFNet has reached the best performance of the mainstream algorithm and achieved better results in tests of segmentation of COVID-19 layer array. The next is the summary part. In this paper, we propose a normal boundary assist and discriminative feature extraction network to segment COVID-19 infected area from CT images. In order to solve the problems of difficult segmentation caused by dramatic changes in the infected area, we use a triple attention model to extract discriminative features for accuracy segmentation. Moreover, we provide an adaptive feature fusion model to model the complementary relationship between shape information and the texture information for clear edge segmentation. That's all. Thank you for your attention.